Hold on. Let me give. I'm just giving remote control to Adrian. Did you have it, Adrian?
I saw the option, but I don't. Okay, I think I have it now.
Okay.
Okay, good morning, everyone. My name is Adrian. I'm presenting here with Eric. We're covering the paper Deepfool, a simple and accurate method to fool deep learning networks. So a quick outline of what we'll be covering. We'll cover what Deepfool is, the algorithm for computing Deepfool, some of the experiment setup and results, our re-implementation of it, and our results and conclusions. So as we know, deep neural networks are really good at classifying images. However, they're susceptible to small perturbations. And the author gives an algorithm that computes the minimal perturbations in order to fool a classifier. Also, they provide a way to evaluate the robustness of a network to adversarial attacks. And also, we find that you can increase your robustness of your model by training on these adversarial images. So quick overview of Deepfool. So on the first image here at the top, this is an image that's classified as a whale. And then on the second row, the image on the right is the perturbation that was generated by Deepfool. And when it's added to the image on the left, it's classifying it as a turtle. But to the human eye, it's still perceived as a whale. And then on the third row, another method that's used to do adversarial attacks that's compared a lot in this paper is fast gradient sign method. So it also misclassifies it, but you can see on the image on the right, it requires a lot more perturbations.
Okay. So in order for the authors to explain the algorithm, they first start off with a binary case of the classifier. So they treat the model as like a linear model case where you have a decision boundary as shown here, where you have a case where it's either the sign is -1 or 1 for the other end. So they give a sample where they have the decision being right here. So in order to change the result, they actually have to like project the gradient past the decision boundary. So what they do is they get the logic value output, which is f of x0. So it's basically the input multiplied by the transposed weights plus the bias, the final output of that. And they compute the loss and get the gradient. So then they multiply it by the gradient, or they divide the logic value by the gradient, and then they multiply it by the unit vector of the gradient, as shown here, which is why you have the L2 norm of the gradient squared. So because it's, models are nonlinear, don't always converge, they actually do this process iteratively until the sign would change. So in order, as an additional thing, in order to get to change, they also multiply the perturbation output that you get from here by scalar, which is 1 plus eta, where eta is a value that's less than 1. So for their project, they used a eta value 0.02, so it would push past the decision boundary. So shown here, they show their algorithm where they take the input and classifier. So in order to change the sign, they just take the model predictions. They just will make sure that the model prediction is changed, and they continuously loop until the sign value is changed from the process here. They don't really show the overshoot value, but the overshoot is they have RI, R sub I multiplied by the overshoot value, and then update the increment. And it's done either until the mass increments that they specify in that function's reached, and it ends the program if it doesn't converge, or if it converges and changes sign, then it ends and returns the final perturbation value. So for the multi-class approach, they extend upon the binary case where they consider multi-class classifiers, multiple binary classifiers, as shown here, where you have like a polyhedron. So in order to get the minimum perturbation needed, they choose the value, the logic value that's the closest to get the other output that's not equal to the model prediction. So they first, of course, get the model prediction output, which is FK x sub 0, which is the argument max, of the logic value, the highest value. And then they loop through all the other logic values and take the difference. So f of k x sub 0 is either the logic value for class label 0, 1, 2, 3, 4, 5, and then their algorithm, they choose a minimum of 10 classes to go through. So it'll be a total of 10 classes to go through. And after they compute the perturbations scalars, where they only taking the absolute value of the with the logic value with respect to the L2 norm the gradient. They then get the index that has the least amount of perturbation needed. And then after that, they compute the final value by taking that index of that minimum perturbation and then multiply it by the unit vector with respect to that. So seeing here, the algorithm works similar to the binary one for multi-class, where they have the image input and then the classifier. They take the prediction output, and then they loop through until like the new prediction output is different from the previous prediction output that they initially got from the model, and they loop through every single gradient based on the number of classes they specify and take the difference, and then they compute the minimum perturbation and use that to compute the R sub I value, and then add the R sub I value to the image plus along with the scalar value for the overshoot. And once they either reach the max iterations or either they change the class label, they end the program and return the value.
Right, so for the experiment setup, the model used, it was the LeanNet model on the MNIST dataset with two convolutional layers, also a fully connected layer with two hidden input layers of the first layer being 500 nodes and the second with 150 nodes was also computed on the MNIST dataset, and both were trained using the gradient descent with momentum. Also, the LeanNet model was used to train on the CFAR10 dataset using 3 convolutional layers. And also the network and network model was used to train on the CFAR10 dataset. And also they used ImageNet dataset that was pre-trained on CAFNet and Google LeanNet models. So the authors devised a method of computing the average robustness of a classifier. So it's essentially taking the magnitude of the minimal perturbation per image and computing the average of it. So they use this to evaluate various models and different adversarial attack methods. So here from this table, you can see Deepfool on the LeanNet MNIST model. Deepfool computes the minimal perturbation required compared to the FGSM model, and then but it requires a slightly more computation time. And on the far right, the paper Intriguing Properties of Neural Networks was one of the first few methods of doing this sort of adversarial attacks. And they were able to get a low perturbation value as well, but the time required to compute each image is much, much greater, at 4 seconds compared to the millisecond level. So across the board here, we see Deepfool for the fully connected model, and the rest, have the minimal perturbations compared to FGSM, and we can see the time is slightly higher, but it does get the minimal. So some experimental results. So each model was trained for 5 epochs using half of the learning rate. And on the right, you can see the test error for each classifier and the attack method. So you can see the test accuracy increases after training on the adversarial images, while the FGSM test accuracy decreases. And we'll see why here in a bit. So when training the LeanNet model on the MNIST data set, we can see the Deepfool robustness increases by about 30%, while the FGSM robustness decreases by 30%. Similarly, here for the fully connected model on the MNIST data set, the robustness for Deepfool increased by 50%, while the FGSM decreased by 35%. And then for the LeanNet model on CFAR 10, for the first epoch, they both increase, but then for every epoch after that, the FGSM model decreases. And then for the network model on the CFAR 10 data set, we see after the first epoch, the robustness increases by 35%, and the FGSM robustness increases by 15%. So the authors had a hypothesis that the more you perturb an image, the less robust your model becomes when training on it. So they did an experiment by increasing the perturbations by Deepfool by a constant scalar here, alpha. So we can see when alpha is 1, your robustness still increases, but as you gradually increase it, your robustness dramatically decreases.
Okay, so for our replicated results of the paper, we first started by training the models on our own system. So Adrian has an RTX 2080, while I have an RTX 2070 Super. So all the inference time I was done on my system. So we're mainly just using mine for my reference card for it. So we tried to replicate the models used in the paper. They didn't really specify the layers, like for the LeanNet model. Also, with the CAFEnet, we didn't have time to implement that because that also required some additional dependencies to install, and I just didn't have time to do that. So for training, we use a batch size 128, but for evaluation, we use 64 because I ran into like a memory bottleneck with the GoogleNet model when processing FGSM perturbations. So we chose 64 for all of them just to make the comparison fair for the inference time. So when training, we chose 50 epochs for models, with the exception of the network and network model, where we use 100 epochs. And we use the learning rate of 1e to negative 3, or 4e to negative 3 for a learning rate, and momentum 0.9. But for network and network, we use the learning rate of 0.1, with the scheduler dividing the learning rate by 10 every 80 epochs. And then some layers of the learning rate for the network and network model actually have a learning rate of 0.01 and a weight decay of -4, and also exception of one layer where it has a learning rate as a multiple of 0.1, which is 0.2. So for our results, we tried choosing epsilon values for the FGSM method that would lead to at least almost close to 90% misclassification. So these were the following epsilon values we used, with 0.6 for LeanNet 5 on MNIST and 0.2 for the fully connected. And for CFAR 10, it actually just needed a small epsilon, so like 0.2 for network and network and 0.1. I didn't further increase for the network and network because it was actually kind of more robust to FGSM. So we kind of stopped at 0.2 because it wasn't really increasing much the further the epsilon value was going. And then for the GoogleNet, we just needed epsilon value 0.02 since it's more susceptible to smaller perturbations, so we didn't have to use like a larger scale like the other models. And then for Deepfool, we use the overshoot 0.02, max duration is 10, and number of classes of 10, because ImageNet actually has like 1,000 classes. So by minimizing the amount of like uh logic values and gradients to process to like 10, it actually shaves a lot of time for the Deepfool method. And so for the Deepfool method, it was actually able to get like close up like 90% or more on average for the test errors. It was, and for the FGSM, we got close with exception of CFAR 10 on networking network, where it wasn't able to go at least near 90. It was actually close to 81%. And then also for the regular training, we're actually able to get close to the other models. For the fully connected, we weren't able to get as close, but for LeanNet 5, we were able to get close as, and DoodleNet, we also had a different value compared to what they have. We're at like 31%, but this might be differences in how the data set was probably normalized. Or either because they used MATLAB for running the DoodleNet model on their project paper. So that's probably why there's a difference, because of the training used for that. So in general, for the FGSM compared to Deepfool, the Deepfool actually has like a minimal perturbation based on the robustness value we got here, compared to the fast range side method. And then also because the system specs are newer, or like much faster, we were able to get like a timing that's much smaller than what they have. So like for the DoodleNet, we did for like 130 milliseconds, but for FGSM, we're actually able to get pretty high in the microsecond range. And then here are some examples for MNIST, where for the fully connected model, where this would achieve actually like the minimum perturbation compared to the LeanNet model. So you can visibly see the perturbations here, but for Deepfool, because it uses the L2 norm, it's actually not as visible as shown, and they're able to both misclassify. And then right here for LeanNet 5, you can also see the perturbations here more visibly than the Deepfool method, which actually has a scale that's much by a factor of 10, or at least close to 10, is actually able to fool the model with the least amount of perturbation. And then here we have results for the ImageNet data set on DoodleNet. I actually had to like amplify the output shown here by a factor 5, because the pixel value has more pixel values, just to show you the difference. So you can actually, if you look closely, but probably you can't see on Zoom, but you can kind of see the noise a bit, but on this one you don't as much. But there are occasions on Deepfool where you can have like these amplified spots here. So like right here, and here you can probably notice, but most of it wouldn't really be noticeable. Like this could be considered like just like a dent, or like in a wall or something. And we also did the adversarial training. We did also have the learning rate, but one of the things we had issue was that Deepfool actually, compared to paper, we didn't actually get improvement in robustness. But this could be due to the fact of how the authors did their training evaluation on it. Where every time we're like going through each the data set, we generate new samples on the go when training it. But I think what the authors did was that they generated the samples beforehand for that first CPOT, then trained on samples, and then they would then get the compare the older weights that they copied the model to the newer updated weights, and that's probably how they did it. But Deepfool, if you always have the new models parameters, it's always gonna make sure to misclassify the updated classifiers. So probably they use the old weights and compare it to new updated weights when evaluating robustness. But for the FGSM method, we were actually able to, by updating using new images, with the model training, we were actually able to increase the robustness with it. So, but for the CFAR 10, we actually found out when training on adversarials that it actually decreases the robustness or accuracy for clean images, which is actually kind of expected. So maybe a way to fix that would be to mix in the adversarials with clean images when training it. So for a conclusion, we were able, given the lack of training parameters in a paper, especially where we're not able to get the same adversarial training results as them, sadly. So in some pros of papers that they actually provide a method to provide the minimal perturbations needed for misclassification, and it does perform faster than the other methods used at the time. And they demonstrate that adversarial training can improve robustness of models. However, some caveats to the paper is that this is a white box attack method. So in the real scenario, you're not really going to have access to model parameters. So you more likely would have to use a transfer attack. So that means the perturbations might not fully work against a model with different, parameters. And especially as if you're getting the minimum perturbations, you also have to factor in compression, like because most images are stored as like JPEGs. So that compression, when you save as that, could probably affect the perturbation and it might not fool the model as much. So any questions?